Hello everyone, welcome to another lessons learned video. In this video we're going to show the mechanism for the hydroboration-oxidation reaction. This reaction, the outcome looks like this. You have an alkene double bond over here, and we're going to add a hydroxyl group to the carbon that is less substituted. So this one is secondary, this one's tertiary. We're going to add a hydroxyl to the less substituted one. So the secondary carbon gets a hydroxyl group and the double bond goes away. And specifically the hydrogen that we're going to add to the other side is going to be syn, or on the same side of the hydroxyl that we add. So if you were to show stereochemistry, it would look like this. You'd get the enantiomer of this as well. So let's show how this occurs. We have the BH3 molecules, which looks like this. We can rewrite it as BH2 and then a hydrogen attached like this. Now this boron atom is going to be slightly positively charged, as it's a little less electronegative than the hydrogens. So it's going to be, it can act as an electrophile really, and these pi bound electrons are obviously nucleophiles, so they're going to attack the boron. And then the hydrogen and its electrons, so really the hydride, are going to attack as a nucleophile, the more substituted carbon. So we're going to get a situation where we have the thing that looked like the alkene. If you imagine this hydrogen as just being red, we get the hydrogen on this carbon. We still have the methyl group, and we have the boron atom with the two hydrogens. Now this process would occur with other boron molecules, or not with other boron molecules, with other alkenes. So another one of these alkenes will come in. The pi electrons attack the boron, the hydride attacks the carbon, and we're going to get another alkene would come in, and the same process would repeat. So the electrons attack the boron, and the hydride attacks the more substituted carbon. Now notice that we have, in this solution, we have hydroxide ions and we have hydrogen peroxide. So independently these are going to react with each other. So hydrogen peroxide can be written like this. You can show the oxygen-hydrogen bond. If that reacts with hydroxide, hydroxide is a strong base, so it will take the hydrogen and then the electrons will go to the oxygen. So we get a situation where we have HOO minus. So now this can come in and react with what we have here. It can come in and attack the boron atom, in which case we're going to get a certain product. Not the whole product of the reaction, but just the product of this this individual event, we'd have the OH attached to the boron atom and the negative charge on the boron atom, negative formal charge. Now we can draw the bond like this. Now what can happen at this point is that for many of these R groups, basically, the electrons will attack the oxygen and then a hydroxyl will leave. So let's show the outcome of that. These two R groups that have the former alkenes on them, they're going to be unaffected, but what's going to be really important is the interaction between these two groups. The OH leaves, so we have, we can draw this a little bit further down. We don't confuse ourselves with everything else that's going on. We're going to get the OH, but the oxygen is still going to be attached, and that oxygen is now going to be attached to this whole R group. So the R group is going to come in like this. So now, at this point, the thing that will happen is that another one of these OOH groups that we generated before, right, like generated like this, they are going to come in and attack the boron. And that will cause, so let's zoom out and draw it. That will give us a molecule that looks like this. So now the boron is negatively charged again because there's 4 groups attached to it. So something has to leave for it to be more excuse me, for it to be more stable. So this R group with the oxygen is going to leave. So that will leave us with, if that leaves, we're going to end with this, and then this can later be protonated by the water molecules that are in the solution. So we have a water, and this would attack. So we will get a hydroxyl group on that carbon. So let's take that, what we just have, and rotate it, right? This is basically equivalent to having this, right? Or you can say having this, if we don't show stereochemistry. If we take this and copy it and go back up and paste it, it looks very similar to what we predicted we would get, right? We would predict that we'd have the hydroxyl on the less substituted carbon, then a methyl that is basically just has a new hydrogen attached, and we can show the hydrogen like this. So that's the whole mechanism for this reaction. You might not need to know it for your class, but if you do, this is how it works. So I recommend that if you're practicing this, just practice drawing it out, and don't just try to look over what I did and try to memorize that. Just try it on a different molecule and see if you could do it without looking at the steps that I showed. But if you can't, just look back, and then once you remember it again, just continue it. And I can give you an example to do on your own. So you can do something like this. You can just do that. All right. So practice it on this one. See if you can get it.